Hello. Hello, everyone. Welcome to the final lecture of Computer Science 2DM3. I hope you're all doing well. It seems that we're missing a bunch of people, so maybe we'll wait a little bit. So I just wanted to let you know that there will be a practice, a review session near the end of as we get closer to the exam. So I saw that you guys have a bunch of exams right before our exam. So we'll try to have two practice sessions, two review sessions, the 16th and the 17th, possibly early in the morning. So maybe 10:30, 11:30. So I think that'll be more helpful. And hopefully I'll have the exam mostly written by then. And then the review will hopefully guide you in the right direction and make sure you study certain things. Okay, ducks. So for today, I just want to wrap up some stuff we left off with. I want to reinforce some things that you've seen. I don't think I'm going to make an exam prep. I think that would cause some people to worry. One thing you could look. Oh. One thing you could look at is the abridged notes, which are no longer abridged, but instead have become extra or extra notes. They have a lot of theorems here that you could look at, right? So in particular, if you go down to the section on relations, there are a lot of theorems here in relations that we did not get to cover in the exercises or in the assignments to avoid making them too long. So there's a lot of theorems here that you can look at if you like. Okay, so you could try proving these. And here's a handy dandy overview. Oh, so much drawings. Ah, that was a useful drawing. So here's a handy dandy overview. So if you're thinking, what should I practice, right? One thing at a time. To get to this, you should look at the previous arrows. So, graph theory and practice. So if you're thinking, oh, I want to study my relations, maybe you should first study set theory, which requires you get familiar with this and get with that and get with that. So one thing at a time. Let's do one of these problems that we did together. I think that will be some fun stuff. So here's the problem. I know we've done these, and you guys seem to have had a lot of fun doing them. So this is the setup you had in midterm 5. So I just brought that setup here for you, and I've given you 200 over 200 practice graphs you can try on your own. So I hope you'll have fun. But maybe let's do one together. So here's let's do practice graph 1 together. Is this one total? Does anyone know? All right. So this is, I'm going to miss doing this with you guys, but last, 5, 4, 3, 2, 1. Is this graph total? Graph number 1. Who thinks it's total? Someone says no. And now you can, you don't need me anymore. You can just hover over it. The answer is no. What about, is it univalent? Is it univalent? All right, so let's last time, I'm gonna miss doing this with you guys. Is it univalent? 5, 4, 3, 2, 1. It is univalent. All right, let's check. Yes, it is univalent. So univalent means equal things go to equal things, right? That very first principle we had, equals go to equals. That is, everything goes to at most one other thing. So here's 1, it goes to 2, it doesn't go anywhere else. So it is univalent. If you look at the 2DM3, if you look at the 2DM3 cheat sheet, these are explained in detail informally as well. So just down here at the bottom, we have that univalent means this this formula that you really want to be comfortable with. Okay, it means this formula, but it also means every node has at most one outgoing edge. Okay, so please do be familiar with these kind of things for the exam. Is it injective? Is this graph injective? All right. So last time, getting all nostalgic here. 5, 4, 3, 2, 1. So this injective means every node has at most one incoming edge, and this is injective. And let's check. Yep. This one is not injective because 2 has 2 arrows coming into it, so no. What about surjective? Is this one surjective? 5, 4, 3, 2, 1. It is not surjective because nothing comes to 0. Nothing comes to 1 and nothing comes to 4. So it's not surjective. It is not surjective. Right. This one is almost surjective, if not for 1. So both are not surjective. And of course, there's many here for you to try out. And you can click on this little link if you want to get the link to it. And if you have questions about them, you can ask in course help. Like this one says it's total. Why is it total? And you might, you can click on the link to get that link, and you can share it on course help, and we can discuss it there. If you find an error, please let me know. And in case you're interested, the code to make this is really, really small. It's not a lot of code. And you can see to check that a property is total, we're saying every element of the every node I has at least one successor. Okay. All right. So at least, at most, these are successors. Now they're predecessors, so they're really dual, as we keep mentioning. So I hope you enjoyed that. I'm gonna miss doing that with you guys, but I hope you'll enjoy doing some of these 200 on your own. So I hope you do that. I hope you enjoy fun. I just want to wrap up with some stuff you're going to see maybe next term. I just want to mention it briefly. Right? So not a big deal, just so you can see it briefly. And please do the course evaluations. Okay, so please do those. And if you have any questions, please let me know. Okay, so as I mentioned earlier at the beginning, in case for those of you who came late, we will have some review sessions on the 16th and the 17th, but we'll probably announce more details as we get closer to that. Okay, dokes. So I mentioned this last time. I'm not going to go in detail over these slides. Post it to Avenue. Yes, I believe the exam is on the 22nd. I can double check for you. December 22nd is the exam. Okay. All right. So I just wanted to go over some stuff that, just to clarify some things, and as well to show you some stuff you'll see next term. So a bit of both, nothing too daunting. So chapter, I think it's chapter 5 of LADM says, hey, another way to look at logic is through these inference rules, right? Focus on them. And many places, in particular in math, this is the way they introduce logic. They say they want to study logic using logic. Whereas in our class, we're using logic as a tool. We're actually using logic to get things done. Okay, so for us, we started off with logics so we can get down to our ultimate goal of proving programs correct. Okay, so we're starting here and we want to get all the way down here. But in other places, they want to use logic for more logic, and then they just stay up here. Right? They're really interested in staying up here. Okay. So you'll see often other places where, for example, we had the weakening rules. So we would say things like P and Q implies P. Right? Please let me know if it's too small. And this is known as the elimination rule, right? So we had another weakening rule which said if you have P, then you have P or Q. These are introduction rules. Remember, we had modus ponens. This is implication elimination. So it's important for you to be aware of these. We had existence introduction or witness. This is another rule here. We had instantiation, right? So a lot of the theorems we had suddenly become the primitive rules for working with these symbols. Okay, so just some things to be aware about. Then to prove something, you want to prove an implication. How do you prove an implication? Well, you assume the first part and go to the second part. That's what implication introduction says. It says to prove an implication, you get the first one, assume it, and show the second one. Okay. So a lot of times these proofs will suddenly become trees. They will branch out upside down though. Okay. So just some things to be aware about. Okay. So I won't stay there too long. So I'll move on. So as I said a moment ago, right, these techniques we've had, right, are the rules, the structural rules we've seen in CalcCheck, right? So or introduction is the for any clause, okay? The elimination, this is the by cases, okay? So this is the actual rule you'll see in other places, and this is what it looks like, okay? So I just want to show you these to get comfortable, but the idea is to get you to write clear proofs. Even if you do so informally, right, you can still be rigorous. Right? You know, in 2FA3, you might not be using CalcCheck anymore, but throughout computer science, you will be writing proofs, at least to check that something terminates, or that something is well defined by induction, or you define something by recursion, you need to prove a property about it. So it's important to write your proofs rigorously, even if you're not going to do so formally. Okay, so that's just something I wanted to mention. Okay, and the last part I want to get to is at the very beginning we kept pushing this idea of programs being correct, and I pushed it a moment ago with this diagram right here at the bottom, and so one of the classes that I used to teach, and the class that before me, the other professor, Wolfram Call, used to teach, is Computer Science 3EA3, Specifications and Correctness. So you might take that in third year. And then all of the propositional and predicate logic you learned is actually rendered using a C notation. So the programming language C. And you can write programs, and you can see here's all this syntax written using those languages. So there are no past exams posted online. So hopefully we'll give you the problems needed to help you out, and we'll point you in that direction. But anyhow, for now, if you can see, we're talking about an algorithm called max element. This algorithm takes some arguments, and here we say there are two possible cases. There's the empty case when n is 0, and then the result will be 0, or there's the other case where it's non-empty. And then remember when we talked in doing proofs by cases, and then we say these are complete and disjoint. So your program will always land in this scenario or in that scenario. Right? And notice here we're talking about a for all integer I, and then here's some property, and then it implies some other property. Okay. And then here's the actual program. It's quite small, right? We just make a loop, and every time we update the maximum, and then at the very end we return the maximum, or the number we started with. We have some invariants, just as you did before in the first few homeworks. Okay, but the reason I want to show you is that this is a real programming language, and these are real assertions, and this is known as from a C, which checks them. So you write real C code, and then in these fancy comments, you write your logic. No proofs needed. You write your reasoning here, and you run the tool, and it will try to find the proofs for you. Sometimes it won't be able to find the proof, and then you'll have to give it some hints, or you might use an external tool to discharge the proofs. But a lot of proofs can be done simply this way. Okay, so you can use what you already know to say, hey, I wrote a program, and I don't want to prove that the program is correct, but I want to say, you know, here's an invariant, here's some properties. Please try to prove it for me. All right, so this is just some exciting stuff that you might see if you take Computer Science 3EA3. You might see a little bit of this if you take Computer Science 3MI3. Some of the requirements classes might also show you a little bit of this. So this idea of proving programs correct is at the edge of most of computing science classes, right? The moment you see an algorithm, you're like, why does it work, right? So you want to know why it works. That is, you want to know if the program is correct. That is, it meets some specification. Okay, so you will constantly see this kind of thing in your programming classes. Okay. Please do stop me if you have questions. Okay. So this is known as ACSL, which just stands for ANSI specification language. So we talked about the Z specification, and then there's also this ANSI, and it really just takes the discrete math we saw, and then it adds on all this programming stuff on top as well, right? So here's I jumped over it really quickly, but here A is an array. It's an array of n elements, and we're saying, is it valid to read from this array, or does this array point to some trash in memory? Okay. Then we're saying we assign, because we're going to alter some of the global state. We're saying we're assigning nothing. We're not going to change anything, and we're going to return a result that's between 0 and n. Okay. And here's some properties about it. Okay. So it's just we're taking discrete math and now we're adding all these programming constructs to it. So this is the next step up from our class. All right. We mostly focused on discrete math, but when you get to ACSL, you add on all this programming stuff. Okie dokes. This is actually used by a lot of different people in our department. So some people use SMT solvers, right, to try to solve really simple proofs really quickly. Others use these verification condition generators. The JML is very popular in industry, Java modeling language. But ACSL is it's very popular. It's been used to verify trains and things. I think there are some companies in Paris that actually make use of ACSL. So it's a real deal thing. Okay. So hopefully, going forward, some of you might encounter. Maybe you won't encounter from a C directly if you don't take Computer Science 3A3, but most likely some of you will encounter Agda, as I've mentioned a few times. Others of you, depending on if you take the software engineering or mechatronics stream, you might encounter PVS. Some of you who are just in mathematics might encounter Lean. And some of you might also encounter Coq, right? So lots of different languages. I think most of you will encounter Haskell. If you don't encounter Haskell, you've taken a strange route in our department and didn't get to see Haskell, I highly recommend you try learning it on your own. Haskell is like CalcCheck, but a functional language. So it's a full programming language, unlike CalcCheck. So you can do I/O, you can write and read from databases. The reason to suggest learning Haskell is not that you might ever use it, which you might, it's a very popular language, but that it teaches you how to write functional code really cleanly. And then you could use that when you go to C or C# or Java or Python, okay? So the ideas in Haskell are very neat. Or you might decide to learn Lisp. Lisp is also another language that allows you to do functional programming, but also lets you do imperative as well. Okay, thanks. So there's also Idris, which is like a halfway between Agda and Haskell, so lots of fun stuff. There's also Isabel or Hall, a popular language in our department. Okay. So there's a lot of stuff we didn't get to cover in this class. We didn't really do a lot on imperative programs, just a little teaser. You'll see that in Computer Science 3EA3. We did a little bit on induction recursion, but not too much. Sequences, you'll get to see more on them. Definitely relational databases, maybe in your third year class on databases. We only touched on graphs. So the graph algorithms from last time, I placed them here for you, right, with some discussions, right? Informal proofs, how do they work? This generalization of in-order traversals, right? Or if you do them backwards, right? And of course, I've presented the code for you, and the code is pretty small. Nothing, depth first search is quite small, right? Not too difficult. So hopefully some fun stuff to learn about. And studying logic for the purposes of studying logic, right? So also known as mathematics, when you study the math of math, right? Or it's called mathematics. And of course, infinite sets. We didn't really talk about them, but what's the size of natural numbers? It's infinite. What's the size of all the odd numbers? That's infinite too. What's the size of the even numbers? That's also infinite. Okay, it seems like we have three different infinities. Are they really different? Well, the odd and the even together should definitely be more than just the odd, right? Maybe not, right? What does infinity mean? What does more mean, right? So lots of fun stuff here. Surprise, surprise, all the natural numbers are the same size as only the evens, which is the same size as only the odds. And if that wasn't weird enough, all of these are the same size as all of the integers. Yeah. So it looks like there's only one infinity, but no. All the real numbers between 0 and 1, there's way more numbers between 0 and 1 than all of the integers combined. So yeah, things get wonky when you talk about infinite sets. Right. You can get like, you know, the Philosopher's Stone when you start talking about the infinite sets, right? The Banach-Tarski paradox says you can take take a ball and then chop it up so small, chop up the ball infinitesimally small, and then when you chop it up, you'll have all these little dust pieces, and from those little dust pieces, you can construct two balls of the same size, right, and the same original size. So that's the Philosopher's Stone right there. Take one gold ball, chop it up so small, make two gold balls of the same original size. All right, infinite profit, infinite money. How does this work? It's because when you chop things so small, the notion of area becomes weird because you're working with infinitely small things. So there's some funny stuff in math. Funny fun stuff. So hopefully by now you've definitely are comfortable with these words: distributivity, idempotency, identity, what a source is, what a root, what it means to be connected, univalent, injective, equivalence, and of course, because someone asked, I did try to put these for you again in terms of simplified English, right, or in trying to explain it in different ways, right? So. Reflexive means elements are related to themselves, everything's related to itself, it means this property, it means this property, it means that property, right? And some of these can be good exercises to prove, right? So a relation is symmetric means the relationship is mutual, which means this. Now for fun, prove it means that. Now for fun, prove it means this. Now for fun, prove it means that, right? Try to show that it means all of these. Right? And there's a bunch of them here I've placed for you, and you can try to prove. You know, like if I have something that's transitive, reflexive, and symmetric, then I can write it this way, and write it this way, and write it that way. So lots of things to practice here for you. Okay. So going forward, right, especially in 2FA3. You definitely need to know what some of these words mean. You definitely need to know what they will mean. In some of your third year classes, you will see types again. You'll see quantifiers again. You'll see relations again. Some instructors don't do things calculationally, like they like to do them with full English style. So that's another thing you'll have to learn, right? A bunch of the other professors in our department do like to use the same Z notation as us. So you'll see that again, right? So just some things to be aware about. You'll definitely see the notions axiom and lemma and theorem again, right? Axiom is essentially definition, right? You can think of it like that. Okay. And you know, you've learned a lot of cool things, and you'll see more. You'll see many of them repeatedly, right? Some of these classes will appeal to some of you. Some of them will not appeal to some of you. But the ideas encountered in our class will show up repeatedly throughout your computing and science education. So hopefully you've learned a lot of cool stuff. Most importantly, hopefully you learned about types and abstraction. You've learned about formality. When you do software, I know I keep mentioning this, but hopefully you've learned that proving is the same thing as programming, right? So hopefully that's something you're very comfortable with. You can tell someone, hey, if I'm showing P implies Q, I'm really writing a function that takes a proof of P and gives you a proof of Q, right? So topological sort was really a constructive algorithm, right? So hopefully you learned a lot of cool things. You saw some cool things. You're aware of some stuff. You might not use it. So remember, Z notation had all those funky arrows. You're aware of them. If you see them again, you're like, oh, I know where to look that up. So hopefully you saw a lot of cool stuff. I hope you had a lot of fun. I hope you learned a lot of things. I hope it's not too daunting. I wish you all the best. And right now, I'd like to leave the floor open to you guys for suggestions on what you want to see. I would like to show you more induction stuff right now, just to get you familiar with that. But otherwise, I'm happy to look at anything else. So who would like to look at induction? So here's induction, structural, like with trees and things. So if you want that, please put likes there. And if you want another topic, please put the topic down and we'll do that. I want you guys to do well, and I think maybe reinforcing induction would be a bit helpful for you. So it seems like people are happy to do induction. If you want to do something else, please let me know, and we'll do something else as well. Okay. So and I keep talking about these real programming languages that let you do real world things. So maybe let's actually do that. So Agda cheat. Oh, let's see where we can find this one. Let's go to about. If we go all the way down here, we'll see there's an Agda cheat sheet, just like we have one for our class. I had the pleasure of making another one for this language called Agda. And this idea I keep mentioning about programming being proving. All right, so here you can see it again. An implication is like a function type. Product types like records and structs and classes and objects are like conjunction, right? Disjoint types are like unions, right? In C and in other programming languages, you might have seen these, right? Implication introduction is like making a new function, right? Modus ponens is like applying a function. So if you're interested, you can come here and look at it. And at the very end, we actually make a real programming language, and we actually run it, and then we ask it for a triangle number, and it gives us a result after we do some compilation. So if you're interested, and of course you've seen these fin types. We talked about them not too long ago. Here's some fin types, right? So just 5 pages if you're interested in some of that Agda goodness. But let's do some induction stuff. So I'll do it in Agda just because it's super fun. So here's our data type. The natural numbers is a set, right? And it has 2 things called 0, and you can make the successor of 0. So this is a real programming language. If you don't like my color scheme, please let me know. There's black. So notice this is a real programming language. It loaded, everything worked, right? So how do we prove a theorem for this, right? What's the induction principle, right? So the induction principle, right? I'll just call it IP, IP/PN. The induction principle says for any property P that you want to prove from the natural numbers to let's say set, right? For any property P, if you want to prove this property is true for all natural numbers n, and you want to prove this property true, then what you need to do first is you need to show me that the property is true for 0, and you need to show me that if it's true for any value x, right? If for any value x I know that the property is true, then I know the property is true for the successor of x. Okay. Okay. So here's the n should be a function type, but it isn't. The successor is from. It takes two things. Okay. So here's the simple property, and notice it's a function now, right? We can define things this way. We can work with it this way, right? Can we see the alternate general form of induction? So this is the simple form of induction just for this is the structural induction one. Aaron is asking about the strong form of induction. The strong form says for all x, sorry, to prove a theorem for all n, when I show Pn is true, that's the same thing as saying for all n, you get to assume, to show Pn, you get to assume that for all m, such that m is less than n, we have access to Pm. Okay, so strong induction says to prove this property, you're proving just Pn. You are allowed to have as assumption this hypothesis that for every m smaller than it, P of m is going to be true. Okay, dokes. So that's the other one. So this is the induction principle, and we can prove properties about it. Let's look at a different data type. So here's and just an example. Here's the number 3. 3 is a natural number. 3 is equal to it's the successor of the successor of the successor of 0, right? So this is the kind of stuff you've seen before, and you can look it up. So that's pretty cool. We can define things as you've done before. Right? So it looks very much like CalcCheck, because hint hint, CalcCheck was inspired by Agda. So a lot of stuff you've seen in CalcCheck works here. Right? So let's put some comments here. Let's make a new data type. Let me just get rid of all of this because it's boring. Let's make a new data type. Data called come to my home. Right? How do you come to my home? Let's call it H for home. Right? Let's see. You're already here. You're already at my home, or you need to take one more step. So take a step. Take a step to get to my home. Okay. What's the induction step for this for this data type? Who wants to guess? So for any property from my home to set, all right. So who wants to guess what it will look like? Who wants to try? All right. So we want to prove that for all h, right? For all h, we have that the property holds for h. All right. How do we do that? We need to have some sort of base case, and we need to have some sort of induction step. So what's the base case? Who wants to try? So, all right, okay. So the base case is we're already here. Okay. Good job, Aaron. And then for the inductive step, we're saying if we go to some place S, right, and we know that it's true for S, then when we take one more step after S, it will be true. Okay. Yeah. So this is because the type H is really just the natural numbers again. Okay. So hopefully that was cool. Let's make a new data type. Slash box. Oh no, slash square. So here's a square, like we're done walking, or we can take one more step. You can take one more step. Okay. So here's a thing. Let's just call this n because of some obvious reason. So here's a data type n. What's the rules? What are the rules here for n? What's the induction step for this type? Who knows the induction the induction principle for this one? So here's an example. Example says go, 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 and you're done. Okay, so go right, go right, go right, you're done. You're here. Welcome to my home. You've walked 3 times and you made it to my home. So what's the induction step? How do you do this? Exactly. Induction, the base case is you're already here. You made it to my home. And if you haven't made it to my home, how can you get to my home? So what's the next? What's the induction? What's the induction step? So suppose you've made it to some place S, okay, and you've made it there. You've made it to some place S. Then, if you go right once more, you should be able to make it. Okay. Yeah. Okay. So to show that P is true for X everywhere, if you take 0 steps, P is true. If you took some steps S and then you go right once more, that's still true, then it will always be true. Okay. It's exactly recursion. It's exactly recursion. So here's a theorem called glue. Glue is from n to n to n. So you glue your, go one path and then go another path, right? So go 2 paths. So go m many steps, then n many steps. How many steps will we have at the end? Let's look at, okay, so we want to write this operation called glue, which means walk m steps and then walk n steps. Okay. Walk m steps and then walk n steps. Okay. So what would we do? Well, we have this induction principle, and the induction principle lets us define things. So let's look at the shape of m. Okay. The shape of m can be either a box or m could be a step. If m is a box, then we've taken no steps, so let's just return n. If m is a step, then what we'll do is we'll go 1 step to the right, and then we'll just glue the rest of the path together. Okay. So as you might have been able to tell, this is just the natural numbers, and glue is essentially just addition. Okay. So you've seen these before. Well, it's kind of cool. And this one and example is really just the number 3. Okay. So the idea is to spot these inductive types even when they look strange and you haven't seen them before. Okay. Shall we keep going in this vein? Do people want to try more things like this? Let's make a new type. Now, instead of going forward 1 step, right? So let me just copy this. Instead of going forward 1 step, maybe you can go left or right. Okay. So you can go. Let me just call it L. Sorry. Let me still call it N, but this time let's keep track of the directions. What streets do we see along the way? So open import data.string. So let's keep track of the streets we see along the way. So this is now going to, I want some data type tau, right? And this is of type tau. And now give me a tau, and then you can take another step, all right, with some directions, okay, and that will produce a step with some directions. So we'll say like this. All right. So what will our example look like now? So let's make a D of string. Okay, so we want to make a D of string. So maybe I'm at James Street, and then I go somewhere else. Okay. From James Street, I go to Jassim Court, and then I finish. Okay. So here I took 2 steps, but this time I wrote down what streets did I see as I'm walking to my friend's house. Okay. So what? Let's try to glue. Let's try to do the induction principle for this type. All right. Who knows what the induction principle will be for this type? All right. So we need to consider all types tau. Okay. So who knows what the induction principle will be for this direction type? You walk, and every time you walk, you keep track of the information you see along the way. Okay. Who knows what the induction principle will be? All right. Yeah. So it's very similar to recursion. Right. So we want to show that a property P is true for all directions D, right? So what will this be? Square for base, exactly. So the property should be true for square. Okay. And then what should it be besides square? What else should happen? So the only ways to make to form a direction is either square, you take no steps, or you write down the information you saw. So you make some information of type T, and then you go right for more directions. Exactly. So the next step says for any path so far. So for any I've made it someplace S. For any of that, I should have some implication. So for any S, if I proved the property is true for S, what happens there? What do I need? So assume I follow the directions. I can follow the directions up to S. Right? Assume I can follow the directions up to S, and the property P is going to be true that far. What else do I need to happen? Good job, Jay. So here's a little hint. D of tau, in our class, we've been calling this sequences of type tau. So really, really close. So someone says we need to do this. Someone says we just need to go another step. Unfortunately, that's a type error, right? That's a type error because this operation, all right, failed somewhere. Excuse me. Let's control R. Okay. Because arrow takes things of different types, right? So you can't give it S on both sides of the arrow. On the first side, it has to be something of type tau, and on the second side, it has to be something of a direction type. Okay. So if you look right here, so that's right. We didn't say what the type of S is, right? So we have to decide, should S be of that type or the other type? So let's say S is a direction piece, and we make a note, right? We have a note of where we are, and that one's going to be of type tau. Okay, so we have those two pieces, so it's a good thing we're using types now. Now what do we put over there? What goes before the arrow? What goes after the arrow? An arrow takes something of type tau, and there's only one thing we have, so we plop that in there. And then over here, we need something of type direction. We only have one, and that's it. Okay. So to prove a property is true for all directions x, we prove it at the very starting direction, and then we say, if I make it anywhere, and p is true, I make it to some direction s, and p is true, then if I take one more step and make one note, then that will still be true, right? So if I have both of these conditions, then I have that it's true everywhere, okay? Because every condition x is going to be either of the shape step, right arrow, or the shape square, okay? And as I mentioned here, you've already seen this before. Square is known as eps, and we've seen this guy before as cons. So you've already seen this arrow as cons before, okay? So let's try to, and here's, so you've seen sequences before or directions. And we can also write our glue function as well. So we said glue before was like this. So now we'll say for any data type tau, if you give me some directions of type tau and directions of some type tau, I'll give you some directions of type tau. Okay. So notice this type is exactly like the natural numbers, but now there's a payload. At each step, we can pick something up of type tau. So in this example, the payload was a string, right? So here we're going to say go one path p and then one path q, right, to get a new path. And of course, how do we define something like this? We define it by looking at the shapes. So what's the shape of p? Let's ask Agda, hey Agda, what's the shape of p? And Agda says, the shape of p can be either empty. Notice this was automatic. All I did was ask. I asked, so here's what it looks like. And I just ask Agda. I say, hey Agda, what's the shape? Look down here, right? I say, hey Agda, what's the shape of p? And it says p can be this or p can be that. Oh, okay. When p is just this one, then I'll just return q. And it goes in there. And when it's like that, there's a note. So let me change this to note. Okay, we have a payoff or a payload, or we have a note. Then we'll keep track of the note, and we'll glue the rest. Okay. And of course, you've already seen this one as well. Glue is essentially catenation. Right? So this catenation operation. So you've already seen these before. Right? Who wants to do one more? All right. All right. So let's try doing another one. I'm glad you think it's neat. And this is a real programming language, right? So let's call this one multiple directions. Let me call it F, because I'm at a fork in the road. When I'm at a fork in the road, so let's say right here, I take no steps. So F, no steps. Or I can take a left, right? I can make a note, and I can also decide to go right. Sorry, no, let's just do this. I make a note, then I pick a direction, and that's it. I'm done. All right. So I can go right. I can go right, or I can go left. All right. Okay. And each time, right before the pointy arrow goes, is where I make my notes. Okay. All right. So let's provide an example of this. All right. Here is an example fork string example. I'm gonna go right, and I'm gonna say I saw I saw Alice, and then I went right. And sorry, this should be an equals. Okay, so I saw Alice, and then I went right, and then I'm gonna go left. But on the way, I saw Kalthum. Right, I saw Kalthum on the way. Right. Okay. And then I decided that I saw Bobbert, and then I go right, and now I'm tired, so I sat down. Okay, so I go right after I see Alice. Okay, this leads me to see Kalthum. Okay, there's no way to draw this to make this look nice. Yeah, so and then from Kalthum I went rightwards. Maybe I can put this down here, maybe make you feel a bit better. There you go. Okay, so I zigzag, right? Yeah. So this is almost like a tree. So I thought I should give you something new, because trees, maybe you've already seen enough of them. So let's form the induction type for this one. So it's not a tree. It's almost like a tree, but it's not a tree. All right. So let's form the type for these. So they're called F. F. So how do we do this? So the induction principle is going to say we have a note, and every time I can make my note and then go right, but I could also make my note and I could go left. All right. So I have two clauses this time. All right. So really, this new data type, f of t, this is really like saying I have a sequence of one kind, or sequence of the other kind, right? It's almost like that, not really, right? It's almost, not really, right? So it's like having two sequences, right? Some of them are right sequences and some of them are left sequences. That's all. So it's just another data type, and you might see it. But anyhow, I hope you had a lot of fun. I hope you learned some cool things. I hope you see that programming is like proving. I've enjoyed being your lecturer, and I hope you also had fun learning with me. And I wish you all the best in your exams. And hopefully, when COVID's done, I will be able to run into some of you, and we can grab a coffee or something. Take care, everyone. Have a happy holidays, and all the best with exams. Bye-bye. I'll be here afterwards to answer questions if anyone has any questions. All the best. Take care.
Thank you so much.